So I'm thrilled to introduce Kathy Yelick from the University of California, Berkeley. Several of us know Kathy, so I want to keep my introduction short, but I want to thank you for accepting this invitation. It means a lot to many of us, and for the inspirational talk that we are soon listening from you. Thank you, Kathy, and you have the...
Thank you.
I think you have your own.
I do not have my own clicker. Well, thank you very much, or as they say, Dankeschön. So
here it is.
I appreciate the invitation to talk to all of you. It's really very exciting to be here. It's beautiful in Hamburg. The weather is incredible, and I know the city is beautiful. And I do want to talk a little bit about post-exascale computing. So I think the whole theme of this conference really is how do we look forward and think about the future beyond exascale, as we're also getting incredible results from the exascale machines that are online and are coming online every day. So I'm going to start just by thanking all of you for first of all, the organizing committee for the invitation, but also many of the colleagues who are in this room and not in this room for some of the work on some of these reports that have been done on post-exascale computing. One is the National Academy's report, and I'll say a little bit about some of the findings of that report as I go through the talk, although more generally I'm going to give some of my own perspective. These National Academy's reports that are done in the U.S. National Academies are really consensus reports, and so the findings of those are really from a larger group of people. There was also a report done in the Department of Energy in the U.S. Looking at the U.S. leadership in high-end computing. So the talk is really divided into three things. The first part of it is going to be about computing demand. That was one of the questions that we've been asked in these kinds of reports. The second one is about some of the disruptions that Michaela has already mentioned to you. And then third, I'll talk a little bit about technology. So the first point I want to make is that the exascale computing program in the US, and this is just the examples that I happen to have handy, have produced really an amazing set of new application capabilities. Some of these are traditional HPC problems, such as accelerator modeling, chemistry, material science, combustion simulation, but a number of them are also in completely new areas to HPC. So the cancer project, the microbiome project, I think some of the work on wind simulations, to do those simulations at this kind of scale is really new. And I think it's really important as we look beyond exascale to think about what are the applications that we should have in another 10 years. So we hopefully will have another 24 applications with completely new capabilities or completely new applications as well. These projects, of course, were put together by large teams. There were 24 projects in this, and I understand that there are also exascale projects all around the world, here in Europe, in Asia, and elsewhere, that really have brought together these kinds of teams to build exascale applications. These rely heavily on the hardware features of the systems, the software teams that built the underlying system software, and as I said, many of them are actually new to the HPC era. So when I look back at the Exascale report and what was put together in terms of planning for Exascale, it's just important to think about how expansive we need to be in terms of thinking about what applications will run on post-Exascale systems. And the report that was done by also people in this room, so that was done in the Department of Energy looking at Exascale. The title of it is Modeling and Simulation at the Exascale for the Energy and Environment. And I think it's interesting that back in 2007, where there were a series of town halls, and I know there were also international meetings like this and discussions about exascale computing, the exascale software stack, and international effort and things, the perspective was still pretty focused on modeling and simulation. And modeling and simulation will continue to be a really important application of high-end systems, but it's not the only application that I think we need to worry about. The other comment I want to make is that I think people often conflate the terminology HPC with modeling and simulation, but also with scientific computing. And I think these are somewhat different things that overlap in many important ways, but are not exactly identical. And so I think we need to be important to think about what we mean by these different terms. So what are the new demands in HPC for science? So beyond simulation, at all scales, and of course higher resolution is always something that we're interested in, getting more fidelity out of the simulations. Problems that just come from large-scale data analysis, and then of course problems that come from machine learning. So briefly, one of the themes, and I think one of the new ideas that has emerged that's related to modeling simulation, but also brings together data and even machine learning, is digital twins. So the idea that you have real-time simulations of a complex, say, physical system that you're looking at, that you're studying, and you combine simulations with sensors, with multi-level simulations, and with real-time data analysis integrated into those simulations. So this is going to drive the need for increased computational capability. Large-scale data analysis, so this is an example I like from the Atlas project here in Europe, looking at the estimated cost of computing. When they estimated that a number of years ago, they misestimated the cost by $1 billion. And that was because, of course, things did not, the computing technology did not continue on the trends that they were expecting, and the data sets after the upgrade of the LHC, and specifically the Atlas project, the Atlas detector, really blew the computing budget. My own project in ECP looked at microbial data. There's data collected from all over the world, for example, in all of the oceans of the world called Terra Oceans. It was collected over 4 years, sailing around the world. I don't know why we don't do that more in this HPC community. Sounds like great fun. They collected over 84 terabytes of data, and that was assembled on 9,000, so basically the entire Frontier system using the GPUs. And this was one of the examples of sort of a new to HPC kind of application. Now, everybody, I'm sure, here is familiar with the way machine learning has driven computational demand and has really increased over the time period. So going back to the pre-deep learning, or I guess we could call it the shallow learning era of AI, when it wasn't quite so successful, by the way, the growth curve was much shallower itself. In the deep learning era, and now in the era of large-scale models, of course, we're seeing just enormous increases. And as a result, it's perhaps no surprise that somebody like Sam Altman is investing in fusion energy, because you really need to think about how are you going to power the future computer systems of these kinds of HPC AI systems. Now, a question, though, is all of this relies on parallelism. So is there parallelism in these kinds of different computational models going from simulation and data analysis to deep learning or to machine learning? So this slide maybe is in honor of Jack and all of the colleagues in linear algebra. The answer is it's all linear algebra, and it always has been linear algebra. So there's a lot of linear algebra, and we do understand the parallelism inside of things like matrix multiply. Of course, we can be a little bit more sophisticated about that and say, well, there's the original seven dwarfs of simulation that look at dense and sparse linear algebra. It also have particle methods, unstructured and structured meshes, spectral methods, and Monte Carlo methods. There was also another National Academies report done a number of years ago on the giants, the 7 giants of big data. They had to keep the number to 7, so they combined dense and sparse linear algebra into one. And this report really was looking at machine learning. It wasn't just looking at kind of conventional data analysis. But what is interesting to me is how much similarity there actually is between these two lists, that something like particle methods, we think of this sort of all-to-all interaction. It comes up in transformers now. It comes up in various data analysis problems in biology where you're comparing everything to everything. And that pattern, when you parallelize it, then has particular ways that you can exploit to optimize communication and so on. In looking at this, we revised the list a little bit relative to that report and put in hashing and sorting as a couple of the areas that we think are really important as kind of fundamental data analysis, whereas integration is more of a higher level algorithm. Now, one of the things that we looked at in the report on post-exascale computing for the NNSA lab, so that National Academies report that I mentioned, was the problem that we've relied, the success of the HPC community and simulation has largely relied on weak scaling over the last decades. And the problem with this is that it has diminishing returns when you look at problems that scale superlinearly. So in particular, something like a fluid dynamics problem where you make the mesh finer. So let's say you increase the mesh resolution by 10x in each of 3 dimensions. So you increase the core count by 1,000x when you do that. But the runtime actually increases because you need to decrease the time step because of the Courant condition. And this comes up in many other cases. We see it, for example, even in something like LU factorization used in the top 500 list, which is why those computations, as you scale it up to get high efficiency on the machine, you see very long running times, and it at times has been almost as much a resilience benchmark as it has been a performance benchmark. Really nice paper by Satoshi Matsuoka and Jens Stomke looking at some of the limitations of strong and weak scaling, or especially looking at the limitations of Amdahl's law, which we all know very well, as well as Gustafson's law, which really gets more at the weak scaling issue. But the point of this is that as you add accelerators to your HPC system, of course, you have efficiency loss, both from loss of complete parallelism between the nodes, but also within on the accelerators within the nodes. And so this graph just shows you sort of how easy it is to get caught in some kind of a bottleneck where you don't get perfect scaling. When we think about strong and weak scaling, I have to say that I think strong scaling is what most application scientists would prefer anyway, because strong scaling, if you can just make my fixed application problem go faster, if I want to, I can run a larger problem. If not, I can just run the same problem faster. And that tends to be very hard to find enough parallelism, though, in a fixed size problem, of course. And on the other hand, for weak scaling, one of the issues, and we'll see this when we look at technology, is in addition to the limitation for these kind of superlinear problems where they just become very expensive still, is that you need to make sure the memory capacity and the memory bandwidth are also keeping up in terms of the scale if you're going to scale those problem sizes. And of course, in really data-intensive things, you also need to scale the I/O system as well. So I think that the conclusion, though, is that there is and always will be an insatiable demand for computing in science. And I mean that very broadly in science and engineering applications. And I mean it in terms of not just simulation, but also in terms of data and machine learning. Parallelism is going to be increasingly difficult to uncover. We've been, I think, very successful at finding new kinds of parallelism as we've mapped these different computations onto accelerators as well as onto HPC systems. But I think that's really the problem that we need to look at. I have no concerns that we can come up with new and exciting things and new scientific breakthroughs with additional amounts of computing. Okay, so let's talk a little bit about the disruptions. And the report looked at really 3 kinds of disruptions. And Michaela mentioned all 3 of them: AI, quantum, and cloud. So I'll talk about each one and not just a little bit of detail for the last 2. So number of reports, again, many people in this room have been involved in reports, certainly in the US, but many around the world, looking at AI in science. There's also a publication from a big international group looking at AI in science applications. So let's just talk about some of the obvious places where AI is already being used. There are many papers at this conference where you're going to see more details of this. First one is analyze. So you can analyze large scientific data sets. Those can be coming from simulations, as in this example, where you're looking at identifying interesting climate features from climate simulations. But you can analyze experimental data. So the next example, you're getting more precision, finding signals in noisier and noisier data, or finer and finer signals from that. So in this slide, which is from several years ago and was looking at traditional kinds of, this was actually starting to look at deep learning, is that it's like adding 4,000 extra tons of detectors. So this idea of being able to use kind of lower resolution experiments and get higher resolution data from them is something that I think is going to change the nature of how we think about putting big experiments together. Co-designing it more with the computations, the algorithms, and the computational systems that we'll need in order to analyze the data. Doing design, so design, in which case for many of the problems that we care about in science, we need to take into account the physical laws. So this is looking at physics-aware learning, and for example, the fact that molecules, if you're looking at something like a convolutional neural net, you really want to take into account the symmetries and the fact that it's rotationally invariant when you flip those molecules around. And of course, automation and self-driving laboratories is a theme that I think we're going to see increasingly as people, especially in areas like material science and chemistry and biology, are able to build automated processes for high throughput experimentation as well as high throughput simulations and computations. So with all of these ideas for using AI in science, clearly the science community should be really wildly enthusiastic about AI in their domains, right? Now, there's of course a few cautionary things we need to worry about. We need to worry about all the kinds of things, hallucinations and things like that that we see when you're using AI techniques. And as a result, in my current role as Vice Chancellor for Research at Berkeley, I get to sort of see the whole perspective across the campus, and it's not just the physical and life sciences, but also in social science and in the humanities and in the professional schools and law and in medicine and in business, where people are interested or looking at AI. But it doesn't always come naturally, and I have now referred to this as sort of the 5 stages of AI. So in each discipline, where we start is denial. And denial is, this stuff is never going to work in my discipline. We are serious scientists here in physics or in biology or in chemistry or in social science, and we're not going to use this crazy AI stuff that we don't really understand. Then there's anger. Right? It's just, I'm really mad. These people are trying to come in and take over my field. They're overpaid. Why are they here? And why do they think that they can have any impact on my science? There's bargaining. Well, okay, we'll hire one assistant professor, but no more than that, right? I am not going to get into this stuff. I think it's going to all fail, and this person will probably never get tenure. There's depression. You start to realize my career is over. It's time for me to retire. AI seems to be taking over. And acceptance, where can I hire some postdocs that know something about AI so they can join my group? So this is kind of what it looks like all over, and you see it happening in different fields, sort of at different periods of time, where people are like really resistant, and then they eventually kind of give in. And what to me is sort of the biggest irony of the whole thing is this includes the AI researchers. Okay, so the AI researchers, they used to do what they were doing, computer vision. They used things like, eigenvalue problems. We love eigenvalue problems. And they would use that for, detecting the edges of objects inside of images. They used all these different kinds of techniques. Or in robotics, they used, these kind of physics-based techniques. And now then AI, deep learning that is, really took over and changed their discipline as well. And so they went through the 5 stages as well. So AI and science, and I won't read through all of the things on this side. I think there's incredibly interesting problems that we need to solve in AI for science. I think there are risks certainly associated with it in terms of that we don't understand some of the why the algorithms work and when the algorithms work, and there's incredible opportunities. And so my conclusion from this, and really I think the conclusion even of the National Academy's report, is that the computational science and engineering community needs to have a leadership role in addressing all of these problems associated with AI and science and engineering. That includes things like uncertainty, quantification, UQ, safety, alignment with human values, and explainability of AI as we apply them to science and engineering disciplines. And that includes, by the way, certainly the social sciences and professional sciences and so on. Okay, so that's a little bit about AI. Let's talk about quantum, and I really just have this one slide about quantum. There's been some really exciting progress, if you haven't been following this, on things like error correction over the last year, with really significant improvements in terms of the ability to build error-corrected quantum systems. And on the other hand, I would say we don't yet have an integrated circuit kind of transistor model yet, right? We've got a bunch of transistors. We've got a whole bunch of different kinds of qubits that you can build. There's still some debate, and in fact, one of the latest big error correction results was actually not for the superconducting qubits, which is what a lot of the early startups were in, but for the AMO physics. And so this is really looking at the fact that we're not yet at a place where we can rely on this for the next generation of computing, which is not to say that we should be ignoring it. So I'm really interested to see how also thinking about how much classical computing we're going to need with quantum, because that's also going to be a big challenge with quantum. So very exciting, but is not replacing also general purpose kind of computing that we do for science and engineering. Now, cloud computing, let's talk about that. This one also gets a lot of hype, as in maybe we don't need HPC anymore because we have clouds. I think there's really important lessons that we've learned from cloud computing. One of them is cost versus price. If you look at the early papers in why clouds are great, they're all about the low cost of cloud computing. They are not about the low price of cloud computing, which is what we actually pay as consumers of that cloud computing, which is, of course, contains profit for the cloud providers. As is appropriate, that's what they're in the business to do. Secondly, that I do think the HPC community needs to think a lot harder about availability and resilience, especially kind of at the scale of an entire HPC facility. How do we integrate our facilities so that as when you're using the cloud, for the most part, you don't worry about your mail going down or your document server going down, because there's so much resilience across sites. And these kinds of major outages that can occur at different sites are still something that I think, and just from normal upgrades, for example, takes down an HPC system. And as we want to integrate it more in real-time sort of digital twin models or other kinds of data analysis models that require real-time, we really need to think about that resilience and how we tie our centers together. And finally, the higher level programming models. I think that this is not about using PGAS models versus using MPI or anything like that. It's using Jupyter notebooks. So we teach at scale thousands of students in a class using Jupyter Hub, Jupyter Notebooks, and we are exporting that curriculum out to community colleges and other small colleges around certainly around the state and even around the country. But we also, it's used in science, right? It's used to actually publish papers where the paper now contains the data and the computational scripts and so on that are used to produce the graphs that are in that paper, which will give us much more sort of reproducible science. So that kind of higher level programming model, I think we really need to embrace in HPC, and has not really been our traditional. So that's not saying old programming models like Fortran and C++ are going to die. It's just, I think no, old programming models never die. They just get buried underneath these layers of abstraction. Okay, so. But really what's important, and this is something the report, the Academy's report really focused on, was what's the important that we need to understand about cloud computing is really the role of the hyperscalers in the marketplace and the role of influence that they're going to have on high-end computing hardware. So the traditional kind of computing, and this is market capitalization, which I realize is not necessarily the best or only metric for looking at the power that people have, but is one indication and one way of kind of quantifying. And thanks to, I guess, Jack and Dan Reed and Dennis Gannon for this particular slide in the analysis. So those traditional kind of computing hardware vendors on the left look pretty small in comparison to the hyperscalers that are on the right. And we've got the big Chinese providers of cloud services and so on in the red there. And the one that does stand out here, which is a hardware provider, is NVIDIA. And of course, that's had a huge increase recently in terms of the market capitalization. And we are seeing that being driven by AI. So what can we see from this? We can see that kind of traditional hardware providers may not have the same kind of influence, and that we may need to think about how do we work with the hyperscalers in the HPC community to make sure we're building systems that are of interest to their market as well as to our market. And of course, that's largely driven, as we've seen from NVIDIA, by the influence of AI. So this is something that I think is a concern. I do think that the HPC community has always punched above its weight in the broader marketplace. That is, what we bring as an HPC community to the design of future high-performance systems is a really deep understanding of applications, algorithms, and how they map onto hardware. And using that kind of insight can really help drive the industry in a way that is outsized size relative to the total number of systems and the value of the systems that we're going to be purchasing in HPC. So I think we need to continue doing that and think about things like how do we want to influence the AI hardware market to make chips that are more interesting and useful to us in science and engineering. So let's switch now and talk about the last topic, which is technology. We'll start with 122 years of Moore's law. So I found this graph, and I kind of like going back to the mechanical age, right? So we can see the exponential growth in Moore's law, going from relays and vacuum tubes up to transistors and the integrated circuit. So this is helpful for kind of seeing where quantum is at, right? It's kind of in that transistor era, but not yet really in the integrated circuit era of growth. But of course, the piece of it that we normally think about is really the transistor density and transistor count. So there's our traditional Moore's law. It doesn't look on this graph like it's necessarily ending. And in fact, there have been many predictions of the end of Moore's law, which have not come to pass, some of them from Gordon Moore himself, and, but also, in fact, there's a couple of them, if you see that on there, with the second one ending in 2025, which is probably where we're going to see where we really are starting to hit the atomic limits of that kind of transistor density. But there's a lot of history here, and but it is something that I think we're going to need to pay attention to. Dennard scaling is long dead, and of course that was the thing that really helped. We leveraged that extensively in the HPC community by having faster clock rates that allowed us to build HPC systems with systems that at least got part of their boost every year, every decade from the fact that we had faster clocks. So years ago on the Parlab project, when I worked with Dave Patterson in the early days of multi-core, he used to talk about performance programming. It's like the Barker-Lounger model of what you needed to do in performance programming pre-2005, because we didn't have to do very much. We could just sit back and wait for the hardware people to do all of the work in terms of making the chips faster. Now, this is, of course, not quite fair. Many people in this room, for those of us who were active in the pre-2005 community, did a lot of work to help make processors take advantage of caches and take advantage of other kinds of hardware features in order to make things go fast. But it was certainly a lot easier pre-2005 than it is today. Now, if we look at the swim lanes for Exascale back in 2008, there were a few different models that were looked at, and there was actually a very detailed report that DARPA had commissioned with a number of us involved in that, looking at how do we build an exascale computer. And the basic model is you take a petascale computer, you use 10 times more energy to run the thing, and then you get 100x more performance per joule, and that gives you an exascale computer. Okay, so that's still kind of a reasonable formula, and we're going to see how that played out. Well, how could we do that? Well, we could do it with faster clocks. Nobody was too optimistic about that. It was already 2008 after all. And wider SIMD, that turned out to be maybe a little bit bigger a boost than we were expecting in terms of the width of those SIMD units. There were, of course, accelerators, which at the time, they were in some of the HPC systems at the top of the top 500 list, but I have to say the scientific community was still pretty much in denial in terms of whether this was going to be useful for all of the different kinds of workloads. And then there was just build a system with 100 times more cores. And now when we look at the Office of Science DOE systems, which give you kind of some breadth of some of the systems out there, although not all of them, what we see are 3 different GPU architectures, all accelerated, all with the same integrator HPC, and this is something that I think we're very concerned about. And while there are other integrators around the world, and there are other architectural models that you see both in Europe and in Asia, I think that this kind of narrowing of focus is something that we all need to be concerned about as we look at the architectures. There's also a nice paper by Peter Kogi and Bill Dally, who were certainly instrumental in that older report, the 2007 report, looking at planning for exascale computing. And this looks back. It's the frontier of exascale, and kind of how did we get there, and how long did it take, and so on. And I've added to this, actually, the first terascale system in a comparison. They were comparing petaflop and exaflop, but looking at things like the technology scaling. So what did we get going from teraflop to petaflop to exaflop? And of course, this is 1D, so this is nanometer scaling. We got 10x. In both cases, roughly speaking. These are going to be very round numbers you'll see in red here. In terms of how much power we're going to use in the system, it increased by about 2x going from terascale to petascale, and about 10x as predicted, right, going from petascale to exascale. The efficiency, we got about 400x going to petascale and about 100x going to exascale. Memory, okay, so those things together kind of give you the fundamentals of how you scale the computational performance. In terms of memory scaling, of course, we have not kept up with 1000x at all in terms of how much memory we're putting on these systems. FPUs, we only had to add 100x more in the going to petascale. We were still getting some of that benefit from clock speed scaling and the early years, at least, of that, whereas exascale is basically entirely adding more floating point units. And there was a big jump in floor space going from tera to peta, but not really going to exascale. There's different numbers of the cabinets are smaller, but they're much larger on the Frontier system. And this is, of course, some of these things are somewhat different with the different technologies, but I think it's helpful to understand if we're going to talk about a Zettascale system or something. And I think one of the points that they make in this paper is maybe the biggest benefit in terms of speed up to science would actually come from making the memory faster and having more capacity, especially of high performance memory on the system, rather than from more floating point. Which is why, by the way, the report didn't really refer to Zettascale. So energy efficiency, by the way, did not track the technology scaling, and this is important because it's really about, because energy efficiency is really what it's about in terms of getting to the next generation of system, because we don't want to have our next system be 1,000 times larger. So, you know, we're hearing about 2 nanometer fabs, so we may squeeze out just a little bit more in terms of chip technology scaling, but it doesn't necessarily correspond to, there's some issues even at the technology level in terms of what you'll get from that, but you'll also are not going to get the sort of energy efficiency scaling, which is the third line there. So here's my straw person version 0 of what we need to get to a post-exascale architecture. So we've got our GPUs, and we've got our specialized AI hardware, and we've got things that are specialized for simulation or kind of more broadly for science and engineering applications. So in the GPU and in the AI space, because of course those GPUs are being largely driven by AI, somewhat more general purpose than the really specialized AI processors, how can we as a community influence them to make AI better? For example, to make the hardware better for what we want to do. For example, supporting sparse memory accesses of some kind to allow us to use them in others. Of course, the narrowing of floating point arithmetic is something else, and I'll say a little bit more about that in a minute. Specialized for simulation, so then this is where we really need to take co-design to the next level and really think about how do we influence and even design and build hardware, not necessarily the entire processor, but maybe accelerators that are designed for the applications that we want to run. This graph is actually from Jensen Huang's NVIDIA GTC keynote talk and is another nice exponential, but as you can guess, it doesn't have much future to it. This is the increased performance of AI, so 1,000x in 8 years, but it starts with 16-bit, has another 16-bit, a couple more of those, then goes to 8-bit and now to 4-bit. So, you know, there's exponentials, but when you're at 4 bits, you're probably not going to get too much further. I guess you can get to 1 bit, which is just a sign bit, and now you just need to know optimize up or down, right? That's all you're going to get. So go think about linear algebra with 1 bit of precision, okay? All right, so you know, specialization, there is a lot of work in you know, the startup community and elsewhere and in the large companies as well, thinking about how you specialize for deep learning applications. I do worry that there's so much focus on it, we're sort of not thinking about all the other things that might come along and might even make AI better, things like graph neural nets. So yes, they may still be deep learning, but are they, do they have the kind of characteristics that we're looking at? And obviously some of the companies are looking at that. But I just want you to remember that there was a time when the LinPack benchmark really represented what we did in modeling and simulation and scientific computing. And we don't run those kinds of enormous dense linear algebra problems at scale, which is not to say that dense linear algebra isn't still important in a lot of the computations that we do. But I think we just have to be careful not to sort of over-optimize for a particular algorithm. So everyone is making AI chips. You've got your traditional chip manufacturers, you've got your software companies that we looked at in that other slide, and you got your startups in this business. Not everybody is selling these chips. So in the case of the startups, they're not selling them because not all of them are actually making money and going to survive in this. In the case of the software companies, though, this is a big issue, which is that you can't just go out and buy the chip. And this is where, in the report, we really thought about how you might need to partner with companies like Google or Amazon or Facebook and Apple and so on to figure out how we might use those for the HPC kind of scientific applications. Now, specialization for the masses, I think we'll probably hear more about that in the keynote on Wednesday and perhaps throughout the talks today, but looking at how have we made it easier to design hardware, right? The problem in specialized hardware historically has been it's so expensive and so time-consuming that you can't keep up with the pace in which things improve for the general purpose computing market. Now that general purpose thing has slowed down a lot, so the balance has shifted, but we still need to have tools and an ecosystem that makes it easier and cheap to to design your own hardware. And things like the RISC-V system or the kind of model and platform and the ARM as well as chiplets so that you're not designing an entire processor are going to be important. So what we came down to in the report was this idea that you really need to think about the technology as well as the marketplace. So it's not just about technology trends, and that combination of those two are really radically different than they were in 2008, the narrowing of the market and these other problems. So what's a post-exascale strategy for the scientific community? It's the beat 'em or join 'em strategy. The beat 'em strategy says we're going to design our own processors for science and engineering. We have to have more co-design. We have to and that includes not just designing chips, but and designing your software stack, the low-level system software stack, and don't forget about the math libraries and things like that. The join them strategy says let's leverage the AI hardware that's out there. Let's either leverage it because we're using AI in science or because we're doing non-scientific, non-AI algorithms, using the AI hardware. So, and that may come from influencing that AI hardware to make sure, and part of that, the sort of sneaky way of doing this is kind of getting embedded in the AI community and trying to convince them that in order to make AI better for, let's say, commercial AI applications, you really want to have certain features like don't throw away your 64-bit arithmetic and things like that. So just to conclude, a post-exascale, it's not business as usual. The computing demands are going to continue to grow. We've got these challenges with both weak and strong scaling. The technology, but also the marketplace have really changed, and we're seeing some of these disruptions, but the one I think we probably need to focus on the most is AI. And finally, there's a lot of other kind of global issues that we need to worry about in terms of how to build and procure large-scale HPC systems. So thank you very much for your attention. It's been a pleasure talking to all of you, and I look forward to having a couple questions.
So we have a couple of minutes for a couple of questions. There are microphones on the stage, and I cannot see anything because of the light. So, but do I see anybody who have question in the audience?
There's one over there.
Okay, so if you can introduce yourself and.
I'm John Simpson. I don't know if there's any other Canadians here, but I'm here to catch us up in the global community. Thank you very much. Question I have is, I think When you showed the kind of the current state of the world in terms of exascale computing, I think you implied that you had a worry that we were seeing too much homogeneity in where the systems are and where they're going. If that's the case, could you say a little bit more about it, please?
Yeah, so a very good question. I think that that may be somewhat narrowly focused on the U.S., but I've seen kind of a single integrator that we've been using for most of the largest scale HPC systems, and the fact that they're all based on different GPUs. So there is some heterogeneity in the providers because one of those systems is got NVIDIA GPUs. That's not an exascale system. That's the Perlmutter system at NERSC. And then there's of course AMD and the Intel-based GPUs systems at both Oak Ridge National Labs and Argonne, and the other NSA labs also have these. And we see different kinds of accelerators in systems around the world to some extent, but I think that I don't feel that there's quite the same level of kind of vibrancy in the HPC community, vendor community, in terms of competition between all the companies that want to provide HPC systems. So I think that's where my concern rests, really.
There was a question from the audience. You can submit your question also through your application. And it was about computing sustainability. It was about the question, what will be the cost of exascale or post-exascale computing from the point of view of power, software, human resources? What should be our concern when we speak about sustainability?
If you're running an HPC center, and of course I did run NERSC for a while, I think the power is now a big, relative to software. I mean, there's the hardware purchase price, there's the people, and there's things like software licenses and power. I think the power bill to me is the biggest constraint, and what I see it trading off against is the amount of money you can invest in hardware, because you need a certain number of people to probably support a community. So that is a bigger concern to me than the sort of software license costs. Of course, most of the application software is open source, so the HPC center is not paying for that. On the other hand, if you look at something like the Exascale computing project, enormous amounts of money went into developing those 24 applications. And so if you think about a program going forward, you really do need to think about the total cost of the applications. And I think that software cost needs to be comparable to the hardware costs as well.
In your talk, you were showing us the presence of industry, the large presence. And so for several of us researchers in national lab, in academia, and the question is, how do we work with industry? Should we work with industry? Where is that we remove some of the conflicts or the risk? Because we speak about democratization of research, but at the same time, industry is driven by a different mission sometimes, which is profit. How will be our future? How should we approach this challenge?
Yeah, I think it's a great question. I think it's really important when we talk about AI. Of course, right now, a big concern we have is that a lot of the AI research is being done in industry because academics don't have access to the kind of computing capabilities that they need. Part of that is this HPC community needs to embrace AI researchers. For example, people doing computer vision and robotics and other problems like that that don't fit our kind of traditional model of what HPC applications are. But I think more generally, we do need to think about how do we partner with some of the big, the hyperscalers, as well as thinking about if we're going to design hardware, parts of the hardware, how do we share the risk of that with the vendor? So very good question. I'm not sure I have all the answers to it for sure.
Is there any other question from the audience?
Yes, I have one.
Yes.
This is Brian Van Essen from Livermore. So thank you, Kathy, a wonderful talk. I agree with everything you said about especially AI and the engagement with the science community and how do we preserve the architectures that we need for our workload. I just want to amplify the statements. I think one of the key things that we need them to remember, the AI community, is that once they run out of sort of natural language, video, and sort of the normal human-generated content, the high-precision HPC systems that we run are what are going to generate much of the scientific content necessary to train new scientific machine learning AI models. And so that coupling and the need for high-precision compute is going to be, existential for them going forward to drive that next advancement.
That's a really great point, and I think that I didn't talk so much about how AI and simulation fit together. One of the areas obviously is in generating the data that you'll use for AI. Of course, another one is improving some of the models by using AI-generated models that get put into the more traditional physics-based models, and driving the simulations with AI. So there's just a lot of places that the two fit together. But I agree that yes, we need to make sure that we don't lose that high precision arithmetic as as they focus on some of the commercial applications.
A question from the audience through our application, a little bit provocative. Shall we replace top 500? What are the metrics in the post-exascale computing that are important? The real execution time? That is...
I see. I actually really like the top 500 list because it provides an amazing historical record of where we've come. It is not perfect. I think it is not the thing we should use to drive machine acquisitions, for example. That's where I think we start running into problems, and certainly we should not use it to design machines. And so we need to be careful that it doesn't become sort of overly important in the whole ecosystem as we think about co-design and things like that, especially if we're going to design our own pieces of the hardware. But I don't think we should get rid of it because when you've got these exponential growths, it's really nice to have a single benchmark that you can use to look back historically. And it says what it says, right? You just need to make sure you understand what it's measuring and not kind of overemphasize it in terms of letting it drive the future.
We have a question from one of our student volunteers, and look at you as a mentor and say, well, if I were your student, which direction would you point me to for my future as a...
Wow, okay.
This is not me, but
That's not you. Okay, well, we might talk about this a little bit more on one of the panels, but I think that that looking at the combination of AI and simulation is really important. I think people need to be adept at kind of all those different kind of algorithmic techniques. I guess, what we look at in general in training students is that list of, the 7 motifs, the 7 dwarfs, whatever you want to call them, the 7 giants now of data, but really trying to make yourself understand the different ways in which you parallelize and get performance out of a lot of different techniques from both an algorithmic perspective and from a hardware perspective, and software, how do you map it onto the hardware? And so I think that having a good sort of broad understanding of that is really valuable because I think things are going to change in the future, and it makes you very adept at being able to work on different applications and so on.
So something again from the audience about the Moore's law, if it is really there. So how should we procure and operate our future system?
If the end of Moore's law is coming, or is that...
if it is there.
Yeah, no, I think we are really. I mean, we're seeing it slow down for sure, and so I think that what we need to focus on is things like the energy efficiency of the hardware and what are their techniques, and certainly, look, the other thing I wanted to just say about Moore's law is we in the kind of software, maybe even hardware architecture and the applications community look at it as if it just automatically happened, right? Like somebody just turned the crank and made these things smaller. There was a lot of work done. There's EUV lithography now to get to the resolution that we're at. Many, many years of research. There's things like FinFETs and so on. There's a lot of device tech level innovations that happen to get us where we are. And so what we're hoping for still is innovations that are not necessarily going to be about transistor density, but will be about energy efficiency, and people are looking at those. So we need to hope that hardware, device level kind of hardware community can still come up with innovations.
A question about democratization and of computing of HPC. Do you have an advice for startups or the question says small guys, how can they compete with the big giants that you were presenting in your slides?
Oh, wow, let's see. So I've got the students and now the startup companies to advise here.
Well, we're quite a diverse group.
I think that startups having a solution that works for some, making sure you kind of know your audience, in this case your customers, and building systems that are really solving a problem that is very clearly needed by a piece of that marketplace. I mean, that's true for the students too. I do think, I get enormous pleasure out of making scientific problems go faster or be able to solve larger problems that are changing the kind of landscape of what people do in observational science and in simulation science or whatever. So really enabling that kind of those kind of end users, I think, is also true for the startup companies.
So again, something from a different point of view, application of HPC to the domain that is relevant to the society, healthcare, climate crisis. And so the question from our audience is about how can HPC effectively sustain these domains and the researcher in this domain?
Well, certainly biomedical research, there's a lot of opportunities for HPC, whether it's things like drug design and medical devices, prosthetics. Precision medicine, I think, will continue to be really important in certain areas like cancer. And looking at climate change, as a long-standing traditional application. I do feel like we need to think more about the climate mitigation techniques, and also as we look at climate simulations, what are the adaptations we need for things like wildfires and sea level rise and those kinds of problems. I think but getting more precise information about what kind of extreme climate events we're going to see, I think, is something also the traditional modeling community at higher resolution and with more powerful kind of simulations can do. I also think that this community has not really been that involved with social sciences broadly, and that as we have more human-generated data evolved, I think is going to be increasingly an HPC problem, certainly bringing in AI to the HPC platforms. And so we do need to think about lots of issues that arise there in terms of bias and privacy and so on that have not traditionally been. I've worked on genomics now for several years, and I say nobody cares about the privacy of the mushrooms and the little viruses and stuff, but they do care a lot about that when you get into some of these social science areas.
Thank you. We have a question from the audience.
Hello, I'm Marek Michalewicz from NSCC Singapore. Kathy, if you could please comment as a person overseeing all of research at the university, and actually it's a follow-up question to what you've just said. I would like to ask you more specifically, where do you see uptake of exascale, larger scale computations in social sciences and in humanities and language studies, and those things that are usually completely outside of our own focus? And also, going back to these global problems, things that encompass more than just climate studies, but things that are of global importance, not narrowly focused on interests of one company or industry sector. Things like human migrations related to climate change and distribution of wealth. And another thing yet, war games. We have studies of sentiments in consumer context, but how is it with sentiment judgment or assessment and scenarios in political context and war and peace situation?
I'm glad I only got easy questions here. But, so let me start with the easier part of this and talk about the how do you get the kind of broader communities of research in social science, humanities, and other areas, do they, to exascale? And I think that this actually reminds me very much of the sort of Beowulf clusters. And in the 90s, I guess, there was this feeling that maybe HPC was not going to be needed because universities were all starting to build these modest-sized clusters or small clusters, some of them in their own departments, sometimes at the university level. And exactly the opposite happened, right? Which is once you made it easier for people to get access to a small HPC cluster, it just kind of whetted the appetite to say, oh, but if I can do that on this machine, what can I do with a machine that's 1,000 times faster? So I do think we need to continue thinking about how, on the technology space, we're driving the kind of technology that's going to be in more modest-sized systems. Of course, we're all trying to get them out of our laboratories because they become way too energy-intensive. I can tell you this is one of our big things right now, is going around and finding where people have stuffed them in their labs, where they've, excuse me, melted the hardware because they've stuffed them in their labs, and how do we get them into a more energy efficient and robust kind of environment. So I see that happening a little bit slowly, where the social scientists and others are going to be using more modest scale, and then we'll find, and part of it is, it's very hard to think, I've often said this in other talks, it's hard to think exponentially, right? It's hard to think about, what would I do with a system that's 1,000 times bigger? So we need to help that community, just as we've helped the science and engineering community think about what would you do with a 1,000 times larger or more refined climate model. So I do think we need some expertise in this community that helps the social scientists and humanities think about those problems. Yes, many other social problems. I mean, certainly that HPC can be used for and will be used for, I think. Lots of concerns about doing that in a responsible way. I think the only thing I would say about that is we need to think about how we build these systems and the centers and so on to be responsible from and kind of think about the safety issues involved from the beginning, but also to be using these to think about things like global migration and how will climate impact migration patterns, and what will that mean for global conflicts and things like that. So really important problems.
Let's see if we have other questions from the audience. Yes, we have a question there.
So Marek from the University of Cambridge. I realized I was standing here that I've basically asked a very similar question last year, but I've heard people talking about the death of HPC, that was really the end of the scale and so on. I personally, if I dare quote Jeff Goldblum, nature will find a way. You might actually end up doing things differently. I'm a particle physicist from my previous life, so doing these very approximated models and so on is quite normal for me. But what I'm concerned with is, as you pointed out in your slide, essentially the hyperscalers now dominate the market on the one hand. On the other hand, they do not actually give the hardware make the hardware available to anybody. They essentially give us the packages that we're supposed to use. And yes, RISC-V is a really great thing. I'm personally a huge fan of RISC-V, but let's be honest, there are very few people in academia who actually design their own chip. So we're kind of getting into the situation, in my opinion, I worry we might be getting into a situation where essentially high-performance computing, as we see it, is actually no longer high-performance computing, because that will be happening in the hyperscalers who will be monetizing that and giving us black boxes. So what do you think is the option for us to actually keep HPC relevant to cutting-edge science rather than just as customers of hyperscalers?
Yeah, I think we should support people using cloud services, hyperscalers for science and engineering problems. And I'm involved in a project called Cloud Bank, trying to do that for NSF. So but I think that we need to make sure we have our own path as well that will be in competition to try to keep the prices under control, because I think that we don't want to just sort of go in. I mean, I just really worry about the profits as you're competing against everybody doing, doing AI training for commercial applications. Then the academics will not be able to afford to purchase those kinds of cloud resources, and we see that already being a big issue where we do need to run our own facilities. I don't see. So you brought up another issue about kind of lack of hardware designers. Big issue. This is a big issue in my department, the ECS department at Berkeley. We've seen a big shift of everybody going into computer science. It's not really computer science anymore. It's AI, right? So they're all way over here on this part, and a really important part. And there's lots of jobs and there's lots of opportunities. But that's not to say that there aren't also jobs doing chip design and doing, architecture and doing other, lower level system software and those kinds of problems. So we have a bit of a PR issue right now where there's so much hype over here. We've drawn away too much of the talent, and I think we need to make sure that we make it very clear that this is what is the Patterson and Hennessy, the golden age of computer architecture, right? A new opportunity for architects to actually have the chance to design things, because it's not all x86 anymore. There really are there is some more diversity in the accelerators, and so I think we need to make that case clear to bring the talent to across that community.
As we are closing this session, a question to you. Is the future of HPC bright?
Is the future of HPC bright? Absolutely. I have no concerns about HPC going away. I have no concerns that it's going to be taken over by the cloud or taken over by quantum or taken over by AI, because of course we're embracing all of these things. And so, I think there are lessons that we can learn from them, and we do need to think about what the future, be very open-minded about the future. I do think that we need to think beyond modeling and simulation at HPC. So that's the one thing that I would say I think is a little bit of a danger, that we get too focused on the traditional application areas. But beyond that, no, I think there's just incredible opportunities here.
Thank you, Kathy.
Thanks.
Join me to thank Kathy for this enlightening talk. Thank you.
Thank you.